Welcome to Medical AI for Busy Doctors, Crucial Concepts in Less Than 10 Minutes. I'm Sarah Jabauer, a physician and informaticist and the founder of Machine Learning for MDs. Today we'll be talking about how ChatGPT works. I'm sure everyone has heard that ChatGPT is going to take over all our interactions with our patients so that we will no longer be needed for many of the activities in healthcare. I don't think that's accurate at all, but let's understand how it works so we can have a deeper understanding of what it's actually doing. GPT stands for Generative Pre-trained Transformers. We know that generative means it's generating or creating something new. Pre-trained means that it's already been trained on some data set. And then there's a transformer piece. What does that part mean exactly? Let's dive a little deeper into that. But first, I just want to note that I created this image of a transformer on a computer with DALL-E 2, which is OpenAI's other artificial intelligence system, which focuses more on images. It's really fun if you haven't tried it. ChatGPT is an unsupervised large language model neural network that was developed by OpenAI. I also want you to know that there are other large language models that use a similar approach. There's a BARD system from Google, and there's Claude from Anthropic. So ChatGPT is not the only form of this new technology, though so far it does seem to be outperforming these other two on most tasks. It's also worth noting that there are a lot of ways that you can do natural language processing. Most of them use some combination of either an encoder to change the words into some kind of number, and then a decoder to decode those numbers back into words. You can see some of the examples that have been used in the past, and each of these is going to do a little better at different kinds of activities. But transformers have really taken over since they were introduced in 2017. The main advantages of transformers are that they can process all the data simultaneously, which makes the process faster, and that they use something called a self-attention mechanism, which can weight the different parts of the data. The attention mechanism lets the model focus on the more important parts and pick up meaning from those relationships between words in much larger data sets, and also allows us to do it faster. So let's take a closer look at the transformer architecture. This flowchart is what you'll see almost everywhere whenever you see the architecture of a transformer. So we'll go from the bottom left up and then go from the bottom right up. You can see that there's some communication between these two sides as well, with these arrows in the attention, meaning that the model can get feedback from the input encoder. The first step is the input embedding. That's just when you change words into vectors. These vectors contains information about the words themselves. First, we change the word or a part of the word into numbers, then determine its relationship with other words with positional encoding. Let's walk through this input embedding. You can see on this graph, for example, that the word for men is near the word for grandfather. The word for child is near the word for infant, and the word for adult is farther from the words for boy, child, infant, and girl. And that's what you would expect to see, similarly grouped words on the vectors. Now, this is a very simple example in a two-dimensional space. What the computer is actually doing is far more complex, with many more dimensions than the human brain can easily grasp. A still simplified version looks more similar to this graph, where you could see the different kinds of books being grouped into different colors and being closer or farther from each other, depending on how similar they are. The next step is positional encoding. This helps establish the relationship of the words to each other. Transformers process all the words in parallel at the same time, so the word order doesn't matter. This parallel processing is actually a huge advantage because it lets it run a lot faster. But if it didn't have this positional encoding piece, the computer wouldn't realize that some words should be next to each other, and that words may have different meanings depending on their position. For example, the man killed the lion and the lion killed the man may have the same number of words, but very different meanings. And very small changes in preceding words can drastically change the meaning also, such as, I felt like I could die, meaning of embarrassment, versus I felt like I might die, meaning of physical threat. Then you add the position and the input embedded vector together to get a new number that represents both the word and its relationship to other words. Now we get to the big advance with GPT, which is the attention mechanism. You'll hear over and over in the GPT literature that attention is all you need. Not this kind of attention that this little kid needs, but the attention mentioned in this seminal paper by Google in 2017. This paper was the first major description of a transformer in the literature, and I like that it says in the paper, we propose a new simple network architecture, the transformer based solely on attention mechanisms. It's so simple, isn't it? The attention mechanism then allows the computer to really pay attention to what's important in the text and to give less weight to less important words. The multi-headed part of the multi-headed attention means that the mathematical process of determining how much weight or attention to give each word is repeated many times. The next section that we'll look at is on the bottom right. When it says shifted right, that means that computer shifts its view to the next word, and then it guesses what the following word would be based on the previous words. Then, of course, we have to change those numbers back into words, which is the output embedding, and then move on to this huge part that you can see involves attention, some math functions, including the softmax function at the top that makes the data easier to handle, and this generates probabilities for probable words in the next sequence. This will produce a probability for different words, and the computer will choose somewhat at random, which can be adjusted based on your preference for how random you want it to be. You can imagine that if it was completely random, it would be all nonsense words, but if they always chose the first or most common word, it would be a really boring text. So some randomness is desirable. So to review, we take some words or body of text as inputs, change them into words or parts of words, which we change into vectors. Some math happens, and then that is the input embedding. We use their position to encode it, so we know where they are in relationship to other words. Then we use a multi-headed attention mechanism and feed this through the transformer. And you can see that some of the encoder does give feedback to the decoder on the other side. Then we go to the bottom right and we shift the computer's view to the right. So we try to have it guess the next word. And we see what the embedded number is rather than a number, and what its position is relative to the words instead of a number. And then we have to go through this attention mechanism again and also do some math at the end to give us a probability for the possible next words. And let's just review how GPT was developed quickly. OpenAI introduced the first generative pre-trained transformer in 2018, and this article by the OpenAI folks. This is a nice table that shows the original GPT with a number of parameters. You can see how quickly these have grown over the years, and the training data, which is also growing rapidly over the years. Every year they've released a new model almost, and let's look specifically at GPT-3, which increased processing power, allowed it to really increase its ability to move forward. Increased data input allowed it to be much more accurate. You can see that it went from 1.5 billion parameters in GPT-2 to 175 billion parameters in GPT-3. And also, the main difference with GPT-4 is its use of human feedback and also that it uses images as well as texts. Notably, OpenAI declined to give specifics about GPT-4's architecture, data, and training, citing security and competitive concerns. So we don't really know nearly as much about how this actually works as the previous models. So today we learned about how transformers work, which is the technology that powers ChatGPT, as well as the iterations of GPT so far. Thanks for joining me today, and I look forward to seeing you next time.